So today we want to look at differentials, and this is really closely related to the linearizations that we just did. We'll actually go back and look at the warm-ups that we just finished here, not initially, but at some point today. So what I have here is just a graph. I called it y equals f of x. I was kind of thinking of a square root of x graph, but it doesn't really matter. It's just some graph, right? If you think about that graph for some value x, right, we're going to have a point on our curve. Okay? From that point on our curve, we can find the equation of the tangent line. Okay, so this is still, just like linearization, we're using a tangent line to approximate. We're just kind of approaching it from a different direction here. What we're going to do is, if we have some other value, a, let's say, that is the distance, doesn't really matter if it's a, but what we're going to do is we're going to still use the tangent line to make a prediction, but we're going to word it differently. We're not going to say what we think the predicted outcome would be. We're going to say that if it changes from this point, if it changes a certain amount in the x direction, which we call dx, we're going to calculate how much it changes in the y direction. Okay, so really just if it runs this much, how does it rise? Just thinking back to the old slope formula. So what you're going to do, what we're going to get here is we're going to get a generic equation, right, that's going to have a dy equals, and it's going to have the dx, which is the amount of change we want to investigate, and have the original x value of where we began from. And this is going to tell us if x changed that much, whatever dx is, 1 unit or a half a unit, it's going to tell us how much y changes. So if it went over 1, it goes up 3. dx would be 1. If it went up 3, dy would be, or if it went up 3, dy would be 3, is the idea there. So I have an example here. This is just from the sheet I handed out the other day. We have, just find the differential. This is dy. It's just called the differential. So the first thing we do is we just take the derivative and we make sure we do dy over dx because we're going to need them both. Okay, so to do this derivative, that's going to be a quotient rule. Right, so let's see what we get here. So we'll have, for this one, we'll have that u would be 2x, u prime is 2, v is 1 plus x squared, v prime is 2x. So then to find our derivative, we get dy over dx equals 1 plus x squared times 2 minus 2x times 2x over 1 plus x squared squared. Again, just using our quotient rule there. And we simplify this. Let's see, that's a minus 4x squared, that's a 2x squared, that's a 2. So let's see, dy over dx is 2 plus 2x squared minus 4x squared over 1 plus x squared squared. And then to clean this up, we get dy over dx equals, 2 minus 2x squared over 1 plus x squared squared. So we haven't done anything new there yet, right? That's not our differential yet. Once you, though, get it simplified, all we do to write our differential, dy, is we just multiply both sides by dx. So the differential here would be dy equals 2 minus 2x squared over 1 plus x squared squared times dx. Barely enough room on the board there. That's the differential. And this is going to tell us, based on this tangent line that we're using, right? It's based upon a tangent line that hits at x. If we want to make a prediction of, x is the value we use for where our tangent line hits, right? And you could have one of these with x and y's in it, then you would use the x and the y from the point of tangency. If you multiply that by the amount of change in the x direction, it'll tell us how much change occurred in the y direction. Okay, so for part B here, we're just going to evaluate dy for x equals -2 and dx equals 0.1. Of course, it has to exist and all that stuff there, right? So you have to kind of pay attention to that. We're not getting too super involved with that. So let's see. So for dy, we're going to get 2 minus 2 times negative 2 squared over 1 plus negative 2 squared squared times 0.1. So again, just plugging in. And it should be pretty simple numbers that we can evaluate by hand. Probably going to change 0.1 into 1/10. I would think there's a pretty good chance of that. And this tells us then that, let's see, this would be, so 2 minus 8 would be negative 6. This would be 1 plus 4, which is 5 squared. And let's write that as 1/10, because it's just 0.1, 1/10. So here we get the differential dy equals negative 6 over 250, which is negative 3 over 125 would be the differential. Now, be careful. It doesn't tell us the y value, right? It doesn't tell us the y value. It just tells you that if you compare, so we're going 0.1 unit to the right of negative 2, and then the y value went down by negative 3 over 125. Okay, but it doesn't actually tell us what the predicted y value would be. To do that, you'd have to find the y value for the original function at negative 2, and then subtract negative 3 over 125. So again, the differential is just this little length right here. Right? It doesn't tell you anything about what that y value would be over there. It just tells you how much it changes from this known point of tangency, how much we move from there. So for today's warm-up, we used a linearization to approximate what the square root of 26 and what the square root of 23 were. So let's compare, and we found that our approximation showed us that, here I can even just show this work here for you. So what we did is we did this problem, right? We wrote the linearization here, which ended up being L of x equals 1/10 x minus 25 plus 5. And we used that to approximate what the square root of 26 was and the square root of 23. So again, here's where I put 26 into that tangent, that linearization equation. You got 5 and a 10. Here's where we put 23 in to the linearization equation and got 4.8 or 4 8/10 or 4 4/5, however you want to say that. So let's compare these two answers that we have to if we would have done it using differentials. So that's what I wanted to show. So the first thing we have as our function is still going to be the square root of x, because we're trying to approximate square roots or differentials for square roots in this case. So we're going to go ahead and take our derivative. We get dy over dx is 1/2 times x to the negative 1/2. And then dy over dx is 1 over 2 radical x. And then our differential would be 1 over 2 radical x times dx. So that would be our differential. Now, we're asked to find the change in y, dy, the differential, when x is equal to 25 and dx is equal to 1. So 25, if you add 1 to it, you get 26, correct? I mean, yeah, that's how you add stuff. So with this one, we'll get that this differential is 1 over 2 times the square root of 25 times 1, because it was a difference of 25 to, so that would be 26. So we get dy is 1/10 times 1. So that tells us the change in y is equal to 1/10, right? So it tells us, and what this means is we were at the point 25, 5, right? The square root of 25 was 5. Tells us if x gets 1 bigger, so now it's the square root of 26, the y value gets 1/10 bigger, roughly, right? It's still an approximation technique. It's still based upon the tangent line, right? So since the curve's down, it would still be an over approximation for that differential, or since it's concave down. So now here, The other question we had is what would be the square root of 23 approximately? So this tells us, again, that the square root of 1 more than 25, which is 26, is 1/10 more than the square root of 25. And then this one would tell us that dy is 1 over 2 radical 25. Again, x is 25 times negative 2. So dy is 1/10 times negative 2. I think we did decimals before, so we have negative 0.2. Because before it told us that when we did the linearization, that it would be the approximate value for the square root of 23 would be 4.8, which is 0.2 less than the square root of 25. So again, they're doing the same pieces, but they have a different information. Now there could be times where maybe you already, I don't know, there was a problem I was thinking about where, say you own a pizza shop and you make pizzas with a 16-inch diameter, right? Your large pizza, and you want to see how much dough you'd save if you went down to a 15-inch diameter. Right? Maybe the customer wouldn't even notice, right? But you're going to save a little bit of dough. Let's see what happens there. So what we can do here is, this also kind of brings us back to some equations. If we're going to find, if we know, so we have a 16-inch diameter, right? And it has some area, and we want to go to a 15-inch diameter. Okay? And we want to see what kind of change this makes, right? What kind of differential we get. Well, we're interested in area, correct? So the formula I know for area is pi r squared, is the one I always tend to use. So let's go ahead and say that r is 8 and that r is 7.5. Right? Now this is the one that we already have, right? But here the radius changed by 0.5, correct? So in this case, we have the change in r is negative 0.5. So we're going to use a differential here. So our area formula as a function of r is pi r squared, correct? I don't even need the r there really, but the area is pi r squared. We want to find the differential, it's dr, or well, sorry, yeah, that's the change in r. We want to find what's the change in area. As we reduce that radius, what does it do to the area of the pizza? Right? How much dough are we going to save by saving dough? Yes, you're in your pizza business. So we could take this derivative. Now r is our variable, so this derivative would be dA over dr is equal to 2 pi r. So then our differential would be that the change in area is 2 pi r times the change in radius. We just multiply both sides by dr. So now what we have, we know this is going to be our, we're decreasing it by this much, but our r value, the thing that's giving us our equation here, is going to be 8. Right? We're going to start at 8, and we're going to, so we just want to know how much it's going to take if we take this ½ inch of radius away, right? That's what we want to see, how much area is that going to take away. So to do this, the change in area is 2 pi times 8, we would confuse us there, times negative 0.5. So let's see, this is 16, this is negative 1/2. So the change in area would be negative 8 pi, whatever that would be, square inches. Okay, so that's how much it would save us for each pizza that went from 16-inch diameter to 15-inch diameter. Now, just to check ourselves here, because these are, we could have just found, well, I guess we're using this, it's not going to give us an exact answer, but it should be near there if we actually found the areas and did it that way. So, questions with that? That would be an example of a differential where We just want to know how much we save. We could figure out how much dough we use, but it's just nice to do the differential, see how much you're going to save there.